Hello friends, welcome to our first tutorial on network visualization using Gephi. So Gephi is an open source tool that enables us to visualize and do quick exploratory analysis on various kinds of networks. In community, Gephi is also known as Photoshop for graphs and it helps us generate really cool visualization for different networks. So the current version that we are going to use is Gephi 0.9.2, which is available for MacBook, Windows and Linux and can be installed as a standard software. There are certain datasets that are also made available with Gephi, and I will post the link to those datasets into the description, and we will use one of the scientific collaboration dataset aid for our tutorial. So without further delay, let us get started with our tutorial on Gephi. So I will start a new project so that we all start from the same page, and I will not save the current project. And if you see here, there are certain windows that would appear as soon as you open Gephi. So one would be on statistics. This would be a graph visualization palette. There is an overview, data laboratory, preview, and we can also we can also generate different layouts which we'll talk about in this tutorial. I have already downloaded the dataset from a Gephi website, again link to which it would be present in the description. So we will start and open that dataset. So the dataset is saved under the name NetScience GML, and once we import it, we will get to know more about this dataset. When we click open, you see that there are around 1589 nodes and 2742 edges, and this is an undirected graph. And this entire information is present in .gml file, which is typically used to save the graph objects or network objects that we use with Gephi. We will create a new workspace, and as soon as we click OK, you will see that a network is created on our screen. This doesn't make any sense in terms of visualization. It doesn't tell what these nodes are, what these edges are. So we'll try to add sense to it as we go or proceed ahead with the visualization. But before we do any visualization, first of all, let's look into some basic statistics. We have talked about degrees or number of connections each node has, and hence we can compute what is the degree distribution as well as average degree of the nodes in the network. To do this, all we have to do is press run, and we calculate that average degree of this network is 3.451. From the origin of this network, we know that this is a scientific collaboration network, and this means that on an average, each network scientist collaborates with almost 3.5 other scientists, and the degree distribution looks like that there are certain nodes which have very high degree like 30, 27, 34, and large number of nodes have a degrees either 0 or 1 or 2, which typically means or hinting towards a power law. However, as I have discussed while talking in scale-free properties, that we have to be little cautious before we ascertain that it's a power law. We have to do certain statistics, but Gephi doesn't give us that much flexibility that we can do this statistics here. And for that, we will use another software or a package in Python, which we call as a network X, to do those kind of analysis. But for time being, let us stick to it that yes, this degree distribution is there, and it gives us some idea, if not complete idea, about the network. Similarly, we can also compute the graph density, and when we press run, yes, it is an undirected graph, so our graph density comes out to be 0.002. Let us look into network diameter. This is a big network with around thousands of nodes, and if we run the network diameter, our diameter comes around to be 17. That is, the two nodes which are poles apart are only, we have to cross only 17 edges to reach from node A to node Z or node Z, and the average path length D average comes out to be 5.82. So this is surprisingly very closer to 6 degrees of separation that we have been talking about. But again, as we said, that this number could be 6, 7, 8, as different networks exhibit different average path lengths. But one thing is for sure, that despite large number of nodes, on an average you are 6 persons or 6 collaborators away from the other nodes. Now with this, let us try to make sense to the visualization. First thing is that what kind of visualization we can look at. We can have all the highly connected nodes towards the center and all the single nodes towards the periphery. And to do that, Gephi offers some built-in features. For example, this Reingold visualization, which is often used to visualize networks, often one such utility where all the nodes which have less number of connections are pushed towards the periphery, and you see that this is a dynamical or evolving visualization, and it takes some time for larger networks, but towards the end all these densely connected nodes would be towards the center, with sparsely connected nodes pushed towards the periphery. Similarly, there is another visualization which we call as a force atlas 2. Again, this is very cool to look at in that how it works, and you can control various parameters that how far this should spread. But again, the idea is most densely connected nodes would be towards the center, and many isolated nodes, as you can see here, we have some small clusters here. In fact, it's a click, almost everybody is collaborating with each other, but they are much smaller than our largest connected cluster or the giant cluster that we see in the network. As soon as you lose out the vision, you should click on this recenter button and it will reset the zoom, and again network will return back to its default configuration. Even if this visualization is cool, it still doesn't tell us where are the hubs and such. To do that, we will use this appearance tab, and we will try to add colors to the nodes, as well as we will try to increase or decrease the size of hubs in proportion to their degree. So the first tab gives us option to color the nodes. Second one gives us option to size the nodes, whereas other two controls the label color and label size, which again we will generate very soon. So let us start with the size first. We want to rank these nodes in their order of degree, such that the minimum node gets size of 1 and maximum node gets the size of 300. As soon as you click apply, you see that these hubs appear. This particular node looks like an exceptionally large degree node, but we don't know who he or she is, so we will try to add some labels to it. Again, even in this cluster, despite the fact it is not a part of a giant cluster, it has its share of a hub where it connects to the other nodes or other collaborators. Now let us try to visualize who these persons are. To do that, there is a button. We'll click at the bottom, which allows us to add labels and IDs. When we add these IDs and click on this text T, we get to see the names. And let us try to see that who this guy is. Okay, so this is Albert Laszlo Barabashi, and we have been talking a lot about Barabashi models. In fact, we are reading the textbook in this course, which is written by Albert Laszlo Barabashi. Another big degree node that comes out to be is Geong H. If you remember, Geong H was one of the first scientists to visualize the modern day WWW almost 2 decades back, and we reviewed about his work when we started our discussion on scale-free properties, which is again available on YouTube. Another big hub comes out to be Newman. Newman is known for his Newman algorithms to detect the community or identify what are the subnetworks present within a giant network, and there are certain modularity based approaches to do that in a faster way. So for example, we can again calculate that what or define that what are the sub communities or sub networks present in a large network. If you remember from our discussions on random networks, we have talked about snowbish networks. In snowbish networks, you will have a distinct community, and this modularity gives us a way, if not exactly, but intuitively, same kind of hidden structure within each network. And when we click on modularity, we get a number on scale 0 to 1, where 0 means that no distinct communities are present, and 1 representing that distinct communities are present within a system. Now when we go to the color, let us try to add color. We again go to appearance, click on color, and we will identify our nodes based on their modularity. So you can think of modularity is that each modularity class represents that they are part of the same community, and when we click apply, that certain nodes which have same color, they might have collaborated a lot among themselves, and it makes sense. Let us try to again visualize this community which is led by Barabashi and see that who are the guys with whom he has collaborated. So Geong and Barabashi of course have written multiple papers together, and we have discussed some of them. There is another name that comes out to be Reka Albert. If you look into BA models, it stands for Barabashi Albert model, where Barabashi of course is Barabashi and the second Albert is for Reka Albert. And similarly, you can add lot of sense when you start looking into these communities, and we would know that either they are part of the same research group or they have written extensive papers. You may even find that some of these participants in a same community, maybe they are PhD students or postdoctoral associates in a network. Here is another visualization that is generated for the same network. So there is something called as label adjust. So it will make sure that all the labels in this network are non-overlapping or at least readable. And again, I have sized them according to their degrees, and colors are as per their communities. And now if we generate the labels and make them visible, you see that there are a lot of points here. And if you want to apply some filters next to statistics, you see some filters. That is, now I don't want to read all these labels. I'm just interested to know that which nodes have degrees greater than 10 or 12. So within topology, you see that there is something called as degree range, and when you click on degree range, you can query based on degrees. That is, I want all the nodes which are between 18 and 34, and as soon as I click on filter, you see that only nodes which have 18 or more connections would appear. And in this case, you see there is Barabashi, there is Yong, there is Olthwai, and some other scientists who have collaborated or have more than 17 connections in this network. So you can start looking into the various measures, whatever applies to your project or your interest. But the point here is Gephi offers a lot of convenience to do a lot of filtering or do queries on network without filtering. As soon as you click on stop, this entire network will appear again. Now if you go to preview is another cool option that helps us to do some export ready visualization. And when I say export ready, that means you can export these as pictures and make them available for your research articles or reports. Now for example, here we want to visualize these edges more prominently, so we can change these edge to 6, and instead of mixed color we will use a custom color of black. And as soon as we click refresh, you see that some nice curvilinear edges are showing up into these networks. And now when you click on export, you can export your file either as PNG file, PDF file, or SVG file. And when you click on this save as PNG, it would ask you the folder and file name, and hence you can export it to an external file which later you can use for visualization. Now we worked here on a data which was already available to us. Another question arises, I am working on a project and I want to visualize my own data. So in what format I should save data, what columns I should have, and how we can import that into the network. So I will use an example from my own research on Indian Railways, where we collected the data for stations and we considered two stations to be connected if there is a direct train running between a pair of stations. So we will get two files, one will contain information about nodes and another file which contain the information about edges. Both these files are made available on my GitHub page and link is available in the description. So let us open our node file and try to see that what it contains. If you open this node file, you see that there are 4 columns. One is ID, second is stations, latitude and longitude, as it is representing a spatial data which has a component of space. Now this ID is very important, and make sure that you have at least these 4 columns if you are working on spatial data, or 2 columns with IDs and labels if you are working on a data that does not have any spatial context. An example of such non-spatial data would be author collaboration network, where we really do not care about latitude and longitude of a data unless you want to see that which countries collaborate more with each other. Now this ID would be used to identify the edges. So if we say that node 1 is connected to node 2, we will have a source target in our edge file which would look something like this, that is source and target, and what are the weights are basically number of trains between a pair of stations and the type of that connection. For sake of simplicity, we model this entire Indian Railways network as undirected graph under an assumption that train that is going from station A to B would also come back from B to A. Now we will import these two files in Gephi and try to visualize an Indian Railways network. To do that, we again go to File, create a new project, and we would not save this current project. So we will get an empty canvas again. There is a button called as data laboratory, which will help us import certain files. So we will do import spreadsheet, and first of all we will bring our node data into the workspace. To do that, we will select our file which I have saved as data with lat long. I click on open, and it is asking certain options. What kind of file it is? It is a CSV file or comma separated file. It has node table in it. You can also import adjacency list, metrics, edge tables, which we will do it when we go to edges, and here we will go with the node table. When you click next, it asks you what are the data types. For stations, we should use strings because these are names. For latitude and longitude, we should either use float or doubles. So we will stick to doubles here, which are the data types for Gephi. As soon as you click on next, it will tell you that this particular number of nodes are 809, and so far it cannot see any edges. And what we will do this as an undirected graph, as I just discussed, and we will import it to a new workspace. As soon as we click next, we see some IDs, stations, lat long imported. So far we have no information about the edges. So what we will do, we'll again go to import spreadsheet, select edges weighted, click on open. Now it is telling us that it looks like these are edge tables, but again, if it doesn't show edges here for some reason, make sure that you select the right kind of table. And when you click on next, it will ask us whether weights are doubles, integers. In our case, they are integers, so you can choose integers from the list, but it would not create much difference even if you go with the double here. Now it is asking us what type of graph it is. Yes, it is undirected graph, and we will append to the existing workspace. If there are any warnings, that is saying that some parallel edges are detected, and it will choose a merge strategy here, but we will not again worry about it for this basic tutorial. So when we go to edges and you go to overview, you see that again a similar graph is created as we did last time. However, this graph has a lot of different information because this represents a real world system. Again, let us go to statistics first. Calculate average degree, calculate modularity, or identify sub-communities or communities within a network, and also let us compute the network density, network diameter, what kind of diameter we get. When we run that, we see that average path length is here is even less than 6, which is around 4, and diameter of this Indian Railways network is 9. That is, you can get from any pair of stations on an average by changing 4 trains, and you can traverse entire network which has a diameter 9. Now this visualization would make more sense if we plot them in terms of geo layout. So in this layout list, we already saw that there is something called as force layout, which will tell us which nodes are isolated and where is the largest connected component. There is another plugin which is called as Geo Layout. So when we select Geo Layout, it will give us option of scale, latitude and longitude, and when we run it, we see something like India is coming up. Now since the size of this map is small, I can make it larger. If I run it, make it 10,000, and you see that this map zooms up. By default, this Geo Layout is not installed in your Gephi. So what to do? Go to Tools, Plugins. In the list of available plugins, search for a name called as Geo Layout. It will not show in my Gephi as I have already installed it, and hence it is showing under the name of installed plugins. But in your case, if you are using Gephi for the first time, it should be available in available plugins. You just select it. For example, I select it, you install it, click on install, and it will ask you certain prompts, and you just say that yes, I accept it. And once it is done, it will ask you that it may pose some security issues because it's an open source software, and then once installation is complete, it will ask you to restart now, restart later. So to enable this Geo Layout, you have to restart your Gephi, but I would not do it right now because I have Geo Layout pre-installed. I will just close it, and hence I see that this Geo Layout would be working once I restart my system. Now again, we will do the similar visualization. Let us try to add colors and we will rank our nodes according to their degree, or in fact we will color our nodes according to the modularity to see that what communities exist. So we will color our nodes as per modularity class, and we go to partition, click on modularity class, and when we click on apply, you see that nodes that have more connections among themselves would have same color. Here you see that this south part of India is strongly connected. That means that many trains that leave in south part of India actually terminates within the southern region. However, there are certain stations which are far apart but are connected to these nodes which are located here, and it is expected that many trains that leave North India would go to South India, and this could be one station which is scattering large number of trains here. Similarly, you see that Calcutta is also having large number of trains and hence is part of this larger community. Similarly, you see that this community, that is Bengal, Bihar, Delhi, they have many nodes of similar colors indicating large number of trains that leave this part of India. They either go on the eastern side or towards the southeastern side of the network. So this modularity offers us first order insights into the arrangement of communities. Now also let us try to change the node size. Now you have learned it. We go to ranking, select them according to degree. As soon as you click apply, you see that some of our stations which we call as hubs appear distinctly. You see Calcutta here, you see Delhi here, Mumbai here, Chennai here and Bangalore here. And to make sure we can enable these stations, and as soon as we click on text, we are able to see that yes, in fact this is Howrah Junction or the big station in Calcutta. This is Delhi, this hub is Mumbai. And when you drag these nodes, you can bring them out for better visualization, but as soon as you click on run again, they will go back. With this, we come to an end to our first tutorial on Gephi. In summary, you can generate some excellent visualization, add first order sense to your networks, and try to validate your data that whether you have collected your data is indeed a network or not. To do more advanced analysis, we will use a package called as Network X, which we will learn in next tutorials. Thank you.